Mark?
No.
Okay, so we are live. So hello everyone and welcome to session 153 of the Latin American webinars on physics. My name is Joel Jones from the PUCP in Peru, and I will be your host today. Today we're having Sven Heinemeyer as a speaker. Sven carried out his PhD at Karlsruhe in Germany, which was then followed by postdocs at DESY, Brookhaven, LMU in Munich, and then at CERN. And he's currently a professor at IFT in Madrid, in Spain. Today Sven will talk about recent hints of new physics at colliders, specifically at the LHC and LEP, which are related to searches for scalars decaying into photons, taus, or B-jets, right? And we're very happy to have him as a speaker today. Now, before we begin, let me remind all viewers that you can ask questions and comments via the YouTube live chat system. And these questions will be passed on to Sven at the end of the talk. So, perfect. We're all yours, Sven. Please share your screen.
Okay. Thanks a lot for having me. Let's share the screen. Okay, and we go to the full screen mode. No. No. Okay, here we go. Very good. Yes. Thanks a lot for having me. I will talk about the possible new Higgs boson at, I put it precisely here, 95.4 GeV. You will see how this number comes about. I will start with some motivation and evidence without the W for a light Higgs boson, come to some possible model interpretation, and finish with the physics opportunities at future colliders, but particularly E+, E- colliders. Good. Motivation and evidence for a light Higgs boson. Let's start, for the ones who are not really fully familiar with everything, with a more general introduction. And I will start with two facts. And this is fact number one, namely that we have a discovery. And these are the original plots that were shown by ATLAS and CMS on the 4th of July, 2012. Where here there's a clear indication at the level of 6 or 5 sigma for a new object at around 125 GeV. And this is already 11 years ago. Now we know much more. We have a discovery of a scalar boson that behaves very much like predicted as in the standard model. Here on the left side, there are some recent ATLAS results. One is always the standard model here, so it's normalized to the standard model for the various production modes. On the right-hand side, two CMS plots, one for the production modes, one for the decay modes, and everything lines up nicely to one. So this is fact number one. But there's also fact number two. The standard model cannot be our ultimate theory. And there are many reasons that you are probably very familiar with. We know that gravity is not included. There is a hierarchy problem related to the mass of the Higgs boson that now we know it exists. There's no unification of the three forces. Dark matter is not included. We don't know anything about why we have the baryon asymmetry of the universe. Neutrino mass not included. And there's also some experimental data. And I always put here G-2 of the muon. We know the caveats, but this is not relevant today. The other points are more relevant. And putting fact number one and fact number two together, there's only one possible conclusion. The discovered Higgs cannot be the standard model Higgs. This is just impossible, logically. However, the real question that we want to ask is, does the BSM physics that must exist have any relevant impact on the Higgs sector? And maybe are there already any hints from the LHC that can give us a guideline we can use as a toy example, etc.? Is there something like this? And if so, which model may be doing it? Good. And the answer, how can we answer this question? There are several ways. Of course, we can measure the properties of the boson that we've seen, like the plots that we've seen just 1-2 minutes ago. And we also must check for additional Higgs bosons, because all these, or nearly all changes also change the Higgs sector and often predict the existence of additional Higgs boson. And here I wrote one should check for additional Higgs bosons above 125 GeV. This is kind of what everybody thinks, but one should also check below 125 GeV. And when you think this is all excluded, we will see about this in a moment, yeah? Because the next point here is below 125, maybe is there any evidence yet? And we'll see about this. Good. This is the motivation. Now let's come to the evidence. And I start with the evidence with a talk that was given by ATLAS relatively recently. This was in June this year, if I remember correctly. Yeah, here, 6th of June. And they presented several new results, but in particularly, they presented new results on the low mass Higgs search in this mode. TP goes to a new Higgs, decaying to gamma gamma. And we've waited for this update of the results for 5 years. The last result they got out, which didn't show anything relevant, I come back to this in a moment, was presented in 2018, and now finally, 5 years later, they used the full run-2 data set to come up with the result, and the result looks like this. And then nearly everybody would say, look, nothing spectacular seen here. Yeah, so maybe I should explain how this plot, what does this plot show? This is the mass of the additional Higgs boson. This is the cross-section times branching ratio in gamma gamma. And then this dotted line or the dashed line is the expected exclusion. And then green is 1 sigma and yellow is 2 sigma. And then this solid line, the solid black line, is the observed exclusion limit. And everything is within the 1 sigma range. Only here it deviates a little bit, and this is the highest axis. I put it in particular on purpose in quotation marks here at 95.4 GeV. And this alone wouldn't have caused any attention. However, the CMS result in the same search channel had been presented somewhat before. And here the full data set looks like this. Again, we have the mass of the Higgs boson, then this cross-section times branch ratio, now divided by the standard model expectation. So the standard model would be here at 1. Again, expected and observed. And here there's one nice peak that can be observed. At ATLAS, it was 1.7 sigma. Here it is 2.9 sigma. And the mass where this occurs is, hold and below, 95.4 GeV, exactly the same as for ATLAS. And this, of course, makes it more interesting. Now, there is another quantity that I have to introduce, which is called the mu value. And the mu value is the cross-section times branching ratio, axiomental result divided by the standard model expectation. So you take the standard model, you put the Higgs artificially to the mass you're interested in this case at 95, and then you divide the observed by the standard model expectation, just to give you an idea how strong the signal is. And here the signal has the strength of 0.33 with a kind of asymmetric uncertainty. But this corresponds to 2.9 sigma. On the right-hand side, by the way, it's the same result, but without dividing it by the standard model prediction. Yeah? So it's more closely related or better comparable to the ATLAS result we've just seen on the previous slide. But the mu value is 0.33 plus 0.19 minus 0.12 at 2.9 sigma. And the corresponding ATLAS value that was not provided, but we read it off from the plot and the presentations is 0.18 plus minus 0.10, 1.7 sigma. Good. May I have one more plot here, which is this one. This is only the CMS result because it looks so nice. This is, again, the mass, and then this is the number of gamma-gamma events weighted in a certain way. And red is the standard model plus background fit. Or effectively, it's the background that one would expect. Sorry, it's the background one would expect. And one can't see anything. Yeah, the data points appear to lie exactly on this line. However, if one subtracts the background component as shown in the lower plot here, then the dash is background only, and then red is background plus signal. One can see this nice peak here at around 95 GeV. And I like this plot particularly because it looks exactly as the first plots in the gamma-gamma mode for the H125 have looked like. So I think it's a particularly beautiful plot. And again, I said this is the new value for the CMS channel. Now one can ask the question, are ATLAS and CMS compatible with each other? And our experimental friends did not try to answer this question. So it's up to theorists to answer this question. And this is the plot that we came up with. Again, the mass, then this mu value that I talked about before. And the black dash is again CMS expected with 1 and 2 sigma. Black solid is CMS observed with this bump here. And then this line here, the central value plus the uncertainty, is the mu value observed by CMS. Overlaid in red, again, expected in dashed and solid observed, is the ATLAS result, again with its mu value here at 1 sigma. And one can see at the level of 1 sigma, there's nice agreement between ATLAS and CMS. And since there's nice agreement, not only in the location, but also more or less in the value that we find for mu here, one can ask the question, what is the combined value? Again, our experimental friends didn't dare to go that far. So we had to do it ourselves. This is the one we come up with. The mu value is 0.24 with this only very slightly asymmetric uncertainty. And then we reach the 3.1 sigma level in this channel alone. And slightly provocative, we know apart from starting from 3 sigma, something like this can be called evidence. And yeah, this is where we are with the gamma-gamma channel in ATLAS and in CMS. Good. Now, this is a very old plot. This is the result from the Higgs searches at LEP. LEP, for the younger ones among you, was an E ± collider located in the LHC tunnel. And it was looking for a Higgs boson in the channel. E ± goes to Z, Z goes to Z Higgs, and the Higgs decays to BB bar. Again, we have the expected limit. We have the 1 and 2 sigma line boundaries here, and then black is observed. And one can see there's only one point where it goes outside the 2 sigma range, and this is the highest axis 198 GeV, but it's the BB bar final state, which is very broad, so it's also fully compatible with 95 GeV. And here this mu value is 0.12 plus minus 0.6 2 sigma. Not much on its own, but it's nice that there's the only axis that came out of the lab searches was located exactly at the same mass in a completely different channel. So one more channel to add here, which is the tau-tau channel. So CMS and ATLAS are also looking for new Higgs bosons decaying to tau plus, tau minus. And this is the latest result from CMS, the low mass region and the high mass region. And then when you show this to people, you can ask them, can you spot the axis? They say, yes, of course, there's an axis here, but can you also spot the axis at 95, 100 GeV, which is not very well visible here, but there's one plot that shows it better, which is this one. This is for a fixed mass of 100 GeV. The observed cross-sectional times branching ratio, blue going to light Higgs, with a decay to tau plus, tau minus. And on this axis here is a different production mode, BB, going to BB Higgs, and then the same decay mode. This is the standard model because there is no additional Higgs boson. It should be at 0, 0. But we see that in the glue production mode, we are something like 3 sigma away, from the expectation that there's no additional Higgs boson. So there's also a 3 sigma axis. Now this was for 100 GeV. It's slightly weaker at 95 GeV. If one goes there, one finds a mu value of 1.2 plus minus 0.5, which is 2.4 sigma. And yeah, this is what we also use as supporting interesting evidence in the tau-tau channel. There's one important caveat that will become important in a moment. This mu value here implies a certain coupling strength of the new object to taus. And there are also other limits, also from CMS mainly. For example, in the TT bar Higgs channel with a light Higgs, for example, at 95 GeV, and the Z Higgs channel, again with Higgs decaying to tau plus, tau minus. So it's the same decay mode. And indeed, these two searches make this new value impossible. Yeah, so something at the lower 1.5 sigma range of this mu value might be compatible with the limits obtained in these two search channels. This one has to keep in mind for later interpretation. But this is the number one gets straightforward from the tau-tau channel. Now, we have three axes at 95 GeV. I repeat here the three signal strengths, BB channel, gamma-gamma channel, and the tau-tau channel, corresponding to these sigmas 2, 3.1, and 2.4. If you look at searches for new particles, it's important to keep in mind that somewhere you expect excesses. It's completely normal. However, these excesses all appear now at the same mass. And therefore, this famous look elsewhere effect that kind of diminishes the local significance to global significance. As a theorist, again, slightly provocative, say that I don't have to take this into account. And assuming that these three channels are effectively independent, one would end up at the level of 4.6 sigma. However, as I said, this takes this at face value and does not take into account the other search channels that would diminish the possible signal strength in the tau-tau channel. But somewhere in the 4 sigma ballpark, we would end up. And in order to test this, one can construct a new chi-square measure. This is what we call chi-square 95, which is simply the prediction of a model in the BB channel minus central value squared divided by uncertainty squared. Same for gamma-gamma, same for tau plus, tau minus. Yeah, and in this way you can analyze different models, see how well they can accommodate such a light Higgs boson. Of course, take into account all relevant other constraints. I'll come back to this in a moment. And the question is it possible to fit all these excesses together in a, let's say, non-contrived model? And this is what I will talk about in the next moments. Now, possible model interpretations. And we can see already here, this is an extended Higgs sector, obviously. We look particularly in one type of models, which is Twiggs doublet model extended with a singlet. And there are several models like this on the market, and I describe here on this slide the so-called N2HDM, which extends the Twiggs doublets, phi1 and phi2, with one real singlet. There's also the S2HDM that we will use later. It has a complex singlet, meaning it has an additional degree of freedom in the singlet here. But this is not really relevant for the investigation that we are doing. As I said, in this model, we have here the standard model-like doublet, an additional doublet and the singlet. Then we have the potential with all the possible combinations, which have these coefficients of lambda. In the Twiggs doublet model, it's very well known that in order to avoid flavor change in mutual currents, one elegant way to do is to impose a Z2 symmetry acting like this, which reduces the number of terms that are allowed in the potential. And in the case of the N2HDM, there's another Z2 symmetry that was originally introduced, shown here. It only gives a minus sign to the singlet to produce dark matter. However, this was only the original motivation. This is broken by the VEF. So in this model, there's no dark matter candidate, which is different in the S2HDM. There, the symmetry structure is also a bit different, but in the S2HDM, the additional degree of freedom in the singlet can actually act as a dark matter candidate. This particle can be stable and indeed can give the correct radial density, but I'll not talk about this much more in this talk. What is important for us? We have in this model 3 CP even Higgs bosons, 1 CP odd. In the case of the S2HDM would be 2 CP odd, and a pair of charged Higgs bosons. Now this is our physics content, our particle content in this model. Now, as I was saying, the Z2 symmetry is needed in order to avoid flavor change in neutral currents, and extending the Z2 symmetry to the fermions, up-type, down-type, and charged leptons gives us the famous 4 types of the Twiggs doublet model, which is exactly the same what we also have here in the N2HDM or the S2HDM. And yeah, I mean, they are defined by the doublet to which the various fermions couple here, type 1, type 3, 4, exactly as in the 2HDM. Furthermore, we start out with 3 CP even states. So I go back one slide. The rho 1, the rho 2, and the rho s are our original states. but because of the potential, they all mix with each other. And in order to arrive at the mass eigenstates, we have to diagonalize this matrix, these three states with a matrix R, 3×3 orthogonal matrix, governed by three mixing angles, alpha 1, 2, 3, completely standard. So we rotate it, and then we arrive at these three mass eigenstates, H1, 2, 3. Very good. Now, using this information, one can look at the couplings of the Higgs bosons in this model and how they change with respect to the standard model. One can look at the couplings to the gauge bosons. It's a combination of the alphas, the R's, and there's also beta. I didn't say it so far. One parameter is tangent beta, which is the ratio of the two VEFs of the two Higgs doublets. So it's V2 divided by V1. This is 10 beta, as in the 2HDM, like in the MSSM or NMSSM whatsoever. Yeah, this famous 10 beta. So beta also enters here. These are the couplings of the CP even Higgs bosons to gauge bosons. And here one can also see the couplings of the Higgs bosons to top quarks, bottom quarks, or tau leptons. These three categories that I was mentioning before. You can see it's always a combination of this R matrix that enters and the sine or cosine beta. Good. This will become important in the next slide. The physical input parameters that we use in the model are the mixing angles, alpha 1, 2, 3, 10 beta. This V, which is a combination of V1 and V2, so V squared, like in this is exactly the V squared in the standard model, is given by V1 squared plus V2 squared, the VEF of the singlet, the mass of our physical particles, the physical Higgs bosons, and one parameter, as in the 2HDM, that softly breaks the Z2 symmetry in the Higgs potential. But this is also not very relevant here for us. Fine. Now, why do I tell you all this? Let's have a look at the gamma-gamma and BB-axis first and see what do we need in order to fit them, in order to describe them in the model. Well, first of all, of course, we have to set one Higgs boson mass to 95 GeV and the second one to 125 GeV. Yeah? We have to be in agreement with the experimental data at the LHC. Now, in order to get the BB bar channel from left right, we need that the coupling of the Higgs to gauge bosons is strongly reduced, which is in agreement with the fact that the Higgs at 125 coupled strongly to the gauge bosons, because of the sum rule that exists there. There's not much space left, and this can be arranged. On the other hand, we also need a large branching ratio of the light Higgs at 95 GeV to gamma-gamma for the CMS and ATLAS axes. And you can think about, for example, putting additional stuff in the loop. I mean, Higgs decaying to photons is mediated by a loop. And for example, the charged Higgs boson can play a role here. However, we found that this effect was always very small. And the only way to substantially enhance this branching ratio is to diminish the branching ratio in the leading channel. And the leading channel, the dominant channel for this decay, is H1 to BB bar. So if we want to make H1 to BB bar smaller, we have to make this coupling H1 BB bar small. On the other hand, we shouldn't make the coupling of the H1 to TT bar small as well. Otherwise, we would reduce also the gamma-gamma mode, which is glue-glue going via top triangle to the light Higgs. So we must not make this one small. And if one then looks at the coupling structures, one sees that in type 1 and type 3, the couplings of the H1 to B quarks and the top quarks is identical. So we can't fulfill these two conditions at the same time. Only type 2 and type 4 can do it. There these are couplings, these modifiers are different, and in principle, they can be used to fit these two axes. Now, how do they differ? They differ exactly by the coupling to tau leptons, where in type 2, the coupling to taus goes like with BB bar, it's then suppressed, whereas in type 4, it goes like the coupling to tops, and it can be enhanced. So the tau channel may decide between these two types, these two Yukawa types of our models. Good. So this is all, this is setting the stage for our investigation. This is why we only look at type 2 and type 4. And then we did a parameter scan, and we did it in the N2HDM and in the S2HDM. And in order to do this properly, we need a lot of tools. And in order to do a little bit justice to these tools, because they are provided by putting many, many years of work by many, many physicists. Yeah, I just mentioned them here. The parameter scan is either performed originally with scanner S, or this is a code that Thomas Biekötter provided, the S2HDM tools. This is also can do the parameter scan in this model for you. Tree-level perturbativity is checked. So this is also done with scanner S or STHDM tools. The minimum of the potential should be the global minimum, checked by these tools, or should be sufficiently long-lived, which is done with the code evade. Of course, all points that we have should respect all the search limits coming from lab, tevatron, and the LHC. And here we use our own code, Higgs bounds, which does all these checks for you in a model-independent way. We have to ensure that the Higgs at 125 behaves according to the measurements at the LHC. Yeah, so all the measurements of the LHC, they are encoded again in one of our own codes, Higgs signals, which needs then input for the decays, like from N to H decay or S to HDM tools, and for the production cross-section as provided by Sushi. And this, again, this code gives you another chi-square, the chi-square 125. Which you can evaluate for the standard model and for the 125 GeV Higgs boson in your model, and you can compare these two values. There can be limits or restrictions from flavor physics, and here mainly this branching ratio, B sub S to S gamma, can be important, or the delta MBS, this oscillation, can be important. And here the charged Higgs boson mass plays a role, where we use super ISO for the predictions. Finally, also electric precision data can be important. Here we focus on the T and S parameters, the Peskin-Takauchi parameters, which is sufficient for our purposes when we look at pure Higgs sector extensions of the standard model. And again, these two codes have been used. Now, equipped with all this, we performed the parameter scan. And what is the result of the parameter scan? Now shown for the S2HDM, left side type 2, right side type 4. We show the mu gamma gamma axis here, and here this is the mu BB bar x. You can see the current ellipse, it's nearly an ellipse because the uncertainties are slightly asymmetric from ATLAS and CMS. In the gamma-gamma channel, it's slightly asymmetric, but this is the current ellipse. Before the ATLAS design came out, we had this gray dashed ellipse from CMS only. Yeah? So moved to higher values, but now we're at this black one. The points that we find in the parameter scan are these, and the color coding tells you how well the Higgs at 125 GeV is in agreement with the measurements at the LHC. 0 means it behaves as good as the standard model prediction, where this here is the chi-square of the standard model. Dark values means it's even better than the standard model, and up to 6.18 to sigma, we allow that this is still very well compatible with the LHC measurements. And one can see that there are all kinds of colors in this one sigma ellipse. Yeah? So this ellipse is highly populated, meaning the model, while being in agreement with all the constraints that I've shown you before, theoretical and experimental, and the measurements of the 125 and the measure of 95, this model does the job for these two channels, BB bar and gamma gamma. Similarly, in type 4, also here we find all these points with the same meaning of all the color codes and the contours. You see less points here, but this is just a scan artifact. We could have scanned longer and found the same number of points, so you can't deduce from the point density that type 2 fits better than type 4. Yeah? Point density doesn't have a physical meaning. But it's important to conclude that type 2 and type 4 can fit the gamma gamma and the BB bar axis simultaneously. Good. Now we look also at the tau tau channel, gamma gamma versus tau tau, type 2 on the left, type 4 on the right. And as expected, in type 2, nothing can be done about tau tau. We don't even reach 0.2 as a new value here, where this is the 1 sigma ellipse. In type 4, it looks somewhat better. In the old 1 sigma ellipse, some points were inside. Now with the new one, marginally it can get there. Not very well, but it comes close or so, yeah? And the fact that we do not find points that are above this 0.5 lines here, just this is the effect of the additional searches in the TT Higgs or Z Higgs channel with the same final state, tau final state. So only type 4 can fit marginally both excesses at the same time. This is our result here. And I come back to the implications in a moment. But first, I like supersymmetry. What does can SUSY say about it? And as we know, the type 2 is needed for SUSY. And as I was also telling you before, the tau excess is most strongly in contradiction with other measurements. And therefore, we leave the tau excess out for a moment. And are there any models with additional singlets that may be able to do the job? Yeah, models with additional singlets. And we look particularly at two of them. One is the very well-known N-MSSM, the MSSM extended by one Higgs singlet. And the other one is so-called new SSM. I'll explain in a moment what this is. It's also the MSSM effectively extended by several singlets. And the question is, can the models fit the excesses despite the strong, really strong additional SUSY constraints on the Higgs sector? And we will see what the answer and one prediction that was made by these models before the last round of experimental results. First of all, the NMSSM, this is already a relatively old paper, but still the result that I like to show. We fix the parameters in a certain way. Details are not important. We just fixed them and then varied some parameters here. And this is again the mass of the light Higgs boson, and then this Xi-B corresponds to our lab channel. And one can see that, yes, for a mass of 95 GeV, we are exactly in the range that we need here. At this 0.12, maybe 0.15, we are for 95 GeV Higgs boson. For the Xi gamma, which is the gamma-gamma channel, one can see that we end up here at 95 at the range of 0.4 or so. Yeah, so both of these excesses can be fitted simultaneously using this, what I call now new gamma-gamma value. I didn't tell you the full history. This would go too long, but originally CMS had seen a mu value of 0.6, and we couldn't get to 0.6. We could only get to 0.4 at most in our model. Yeah, this was the result in the NMSSM. And it looks very similar, as I can tell you, in the mu SSM. As I said, I have here two lines of introduction. It's effectively the NMSM, really with 3 singlets more, plus some well-motivated R parity violation. And via an electroweak seesaw, one can reproduce the neutrino data. This is why the model was constructed about now how many 17 years ago by these two professors here. And yeah, this is the mu SSM. And again, can this model fit the excesses? Again, we fix the parameters in a certain way. Details are not important. I have here the results in the plane of one of two of the parameters, mu and A kappa, from the Higgs potential. This is the mu gamma gamma value, which those days we call mu CMS because ATLAS didn't have a result. And one can see that here in this part of the parameter space, yeah, we are more or less in the same ballpark, in the right ballpark, if one looks at the new gamma gamma value between the new mu gamma gamma value is, the very new one is 0.24, but around 0.3 or so is easily reachable here. And this is the lab result, the BB bar channel. Again, one ends up more or less in the right ballpark here, a little bit on the high side. Yeah, so we find effectively what we found in the NMSSM. This BB bar channel comes out a bit high and the gamma gamma channel comes out a bit low. And the reason is that all these restrictions in the Higgs sector of supersymmetry, they force a strong relation between mu gamma gamma and mu BB bar, which we plotted here some years ago in this mu SSM. You can see this is it's a very strong correlation and enforced by supersymmetry. And there one can say that lab enforces that this mu gamma gamma value should be smaller than 0.35. So I was telling you, originally it was at 0.6, but those days the SUSY model interpretation told us that if SUSY is realized, the mu value must be smaller, otherwise it's incompatible. And what happened then in later years, I don't have the plot here, but what happened is that it came down from 0.6 to 0.3, and now even if in the combination 0.24. Yeah? And 0.24 here would even be, well, this is the right ballpark. Yeah, this is where we have to end up. And here both axes can be described nearly perfectly by our supersymmetric model. Very good. I come to my last part. What can we learn from future measurements? Yeah, if there's something, what can we see in, what is the prediction for future experiments from these axes? How can we investigate it? Well, we can continue, and we will continue with the measurement of the couplings of the HL-LHC at the LHC and the HL-LHC, but also at the future plus minus collider. I always write here ILC because these are the numbers that we actually used that I will show to you in a moment, but effectively in this context, ILC means International Linear Collider or NAE plus or minus collider that operates at 250 GeV center of mass energy. Okay, so we can measure these couplings. However, of course, we can also directly produce this new Higgs boson at the LHC, HL-LHC, or at future plus or minus colliders. And if we can produce it there, this will also allow us some detailed, or this hopefully this will allow us to do some detailed coupling measurements of this new Higgs boson at the future plus or minus colliders. One could also look at the production of other BSM Higgs bosons, but this is too speculative. Yeah, so I will focus on these two possibilities. And just for the people who are not familiar with this, I have one slide about a possible plus and minus machine. This is one of the linear ones at the ILC, International Linear Collider, which if it's constructed, then most likely in Japan, but they take a bit long with their decisions there. It would start operation at 250 GeV and could be extended to 1000 GeV. Two detectors, it has polarized the plus and minus beams, which is very interesting for many physics analyses, and it has tunable energy. So it makes it very versatile collider. Yeah? And so we collide them, and here we hope to produce the new Higgs boson. I come back to this in a moment. But let's first have a look at what can be seen, whether this kind of new Higgs boson could be seen at any plus and minus machine. And here I have a plot where, again, the mass of the initial Higgs boson is shown relative to the coupling of the Higgs boson to Z bosons divided by the normalized standard model value squared. So 1 is the standard model here. And now this blue line here, this blue area is the one excluded by lab. This corresponds exactly to the lab line that I've shown you before, where here this small axis of 2 sigma is located. We'll see it a bit later. And now they have been done an analysis for the ILC using either what's called recall method or the traditional method with the BB bar final state. I will not go into details here, but one can see that substantially smaller couplings can be investigated, particularly here. Yeah, so really a much larger parameter space, much smaller couplings can be investigated. And this is important for the production of such a new object at the plus and minus collider. Good. How could one see it? And this is a very nice plot, I think. One could see it via this type of process. The plus minus goes to Z, and the Z radiates the Higgs, and the Higgs decays however it wants. Yeah, it can decay invisibly. We just do not care. We just look at the recoil of the Z. This is how the initial measurements at the plus minus collider for the 155 GeV are supposed to take place. And then one has several standard model backgrounds shown in green here, depending on the mass of the reconstructed object. And here, for example, we have the Z background. This is the 125 GeV Higgs background. And these colored spikes are the expected signals depending on the mass of the additional object here. And for example, this one here is 95. It's located here. It's very close to the Z, of course. This was to be expected. But I think looking at this plot, it's conceivable it can be distinguished from the Z. And of course, this kind of analysis has been taken into account to produce this kind of limit here. But this is the channel how one could initially see it, even without looking at the decay of the Higgs boson, the new Higgs boson. But then one can probably also do some analysis of the Higgs boson decays. I'll come back to this. But first, I show you one plot going back to the H125. I said this is the first thing one can do. One can measure, one can continue to measure the couplings of the H125. Here, coupling to tau plus tau minus versus the coupling to gauge bosons. This is the cloud that we predict in the S2HDM type 2. This is the cloud that we predict in the S2HDM type 4. And this here is the standard model point 1, 1. Green dotted is the precision one can expect at the high Lumi LHC. So if standard model is realized, these models would be excluded at the 2 sigma level, or vice versa. If one of these points is realized, the standard model would be excluded at 2 sigma or more, depending on what is realized. If one includes also a plus and minus measurements, which are of course much more precise, and on top of that completely model independent, one gets down to this pinkish ellipse, and here something like 5 sigma or so can easily be established. Yeah, so high Lumi LHC can get you to the 2 sigma level, whereas the E plus and minus precision, the RLC precision, can get you to a 5 sigma deviation. So that imagine one of these points here is realized, would have a large, the standard model would be ruled out with a very high significance. On the other hand, it may not be possible to distinguish the two types from each other, depending which point is realized. If this point is realized, yes. If this point here is realized, probably not, because they're too close to each other, these two clouds. However, I told you that also this new Higgs boson can be produced as in the plus minus collider. This is again, this effectively this plot I've shown you before. This is the mass, this is this coupling strength modifier. This is the lab observed exclusion, the blue line. The yellow dotted line is lab expected. This was this 2 sigma axis, and our axis of points sits exactly here. This is the limit up to which the ILC 250 could explore or could find this new particle, and we can see all the model points are far above this green line. Meaning, indeed, with the coupling that we have to gauge bosons, this Higgs boson would be produced about, or can be produced abundantly, and then one can ask the question, can we measure the couplings? And I have 2 more plots before I conclude. In this plot, we show the relative precision that we can expect for a certain decay mode of or the coupling of the H1 or the H95 to a particle X, and X can be B bar, tau plus, tau minus, blue blue, WW or ZZ. These 4 are determined from the decay, whereas ZZ is directly measured from the production of this new Higgs boson. Yeah? And there we have a lot of events, and therefore this is the most precise measurement. Or the others, they range between something like 2 and 8%. The only difference we can observe is in the tau-tau mode. The reason is that in type 4, we produce many more taus, and therefore the measurement is more precise, whereas in type 2, we produce less taus and the measurement is less precise. Yeah, this is to be expected. What about model discrimination? This is the final plot I want to show you. Now, coupling of the H95 to tau plus, tau minus versus H95 coupling to gauge bosons. The blue ones are the cloud from type 2. The orange one are the cloud from type 4. And these little shaded ellipses are the anticipated precisions on each point that is realized here. And one can see that the 2 modelizations are clearly distinguishable. Yeah? There's no overlap between one of these points with the other group whatsoever. So this shows that the high precision measurements that can be performed at a future plus minus collider for such a light Higgs boson will enable us to say a lot about the underlying structure, about the Higgs sector, about the coupling of this new object, and this may allow us to really pin down the Higgs sector that is realized in nature. With this, I conclude. I told you there's evidence for Higgs boson 95.4 GeV in the gamma-gamma channel alone from CMS and ATLAS combined 3.1. If one adds in the lab channel and the tau-tau channel, one ends up at above 4 sigma. Possible model interpretations. I first looked at 2 HDMs extended by a real or complex singlet. And the possible explanations, the gamma-gamma and the B-bar channel can be described equally well in type 2 and type 4, the tau-tau marginally in type 4. Looking at SUSY models, I showed you the NMSSM and the mu-SSM, SUSYs with additional singlets, and here gamma-gamma and B-bar can nicely be described, provided the mu value of gamma gamma is at the level where it is now and not where it was a few years back at 0.6. This cannot be explained in supersymmetry. In the future, we can measure the properties of the HL-25 at the plus minus colliders, and there are precision measurements of the couplings that can distinguish these singlet extensions from the standard model. This will be possible at the several sigma level, no problem. The distinction between these two types may not be possible, depending on where we are in the parameter space. However, we can also look at the production of this new particle, and this can be done at the ILC 250 or a plus or minus collider operating 250 GeV center of mass energy, can be produced abundantly. The precisions of the couplings are at the level of 1 to 8%, where the coupling to Z bosons is best from the production mode, and the coupling measurements in the combination of these two can clearly distinguish these two types via the high precision possible at future E plus or minus colliders. And with this, I conclude. Thanks a lot.
Thank you very much for the very, very nice talk. I was wondering if anybody in the audience has got any questions. I have a couple, but let's. Oh, Nicolas. Okay, there you go.
Well, I had a question, but after this last slide, maybe no.
After this one, you don't have any questions anymore?
I'm kidding. Thank you. Thank you, Sven, for very nice and very clear talk. So I was wondering, why do you? I mean, if you throw this excess, why are you calling it Higgs? What I have in mind is the experiment giving us some ideas about the spin? For instance, it has to be spin 0. It has to be CP even.
These are very good questions, and indeed, I think spin 0. It could also be a spin 2 particle in principle. From the decay to gamma gamma. We know all this discussion that we had for the H125. Higgs is for me the most natural thing, because we expect extended Higgs sectors for many reasons, not only for this one, also for example, Byron symmetry in the universe or so, or as I was saying, we could also give us a dark matter candidate, etc. Extended Higgs sectors come kind of naturally. And particularly if you are a fan of supersymmetry like I am, then also extended Higgs sector comes naturally, and you are not. Okay, but I would say Higgs extensions come naturally. They are really in the focus of today's BSM analysis. There are models which do not really extend the Higgs sector, like radion models where the radion mixes with the Higgs or so. I think there was an analysis very early also looking at radion models, but this has not been followed up. So I think nearly all explanations that are on the market, and Thomas has this nice overview, I could have put it in, of all the models that have investigated this. There are, I don't know, something like 20, 25 papers by now looking at these excesses. And most of them are Higgs sector extensions, nearly all of them. Thomas, do you remember any non-Higgs extension that has been analyzed recently? I don't know whether he's still here.
Yes, I am. Can you hear me?
Okay.
Well, I think most of it is Higgs extension. The only difference is maybe that in some cases it's a pseudo-scalar instead of a scalar. So
yes. And this is one thing we also have to discuss in our collaboration in a moment. But exactly. But if Thomas, if you have another, no, Thomas. So what was your name? Bernal. Nicolas. Sorry. If you have a different model in mind that you think would fit, I would be happy to see this, how this works out. Here, as I said, it comes out of naturally. You don't have to twist the model. You don't have to go to, well, of course you have to get the right couplings, but you don't have to go to parameter regions that appear unnatural or so, I would say. That comes out naturally. When you remember the 750 GeV axis, I think there was no model on the market that was neither contrived, or either a model was contrived or it had to go to a very specific part of the parameter space, a very fine-tuned one to explain these excesses. This is not the case here. Here we are really in a normal parameter space, which makes it attractive, I think.
Okay. Thank you very much. Yeah, I have other questions, but maybe you can go to other people.
Okay, anybody else has got any questions? There are a couple of questions from the audience also, but let me ask first a question myself. So can you go back to slide 13, please, where you were showing this yeah, this one, right? So here we do see that production of this scalar with the two the B-jets is disfavored, right?
Yes.
So wouldn't this kind of like suggest that combining the data with the taus and that from LIP is destined to fail to begin with?
Not necessarily, because also for the gamma-gamma mode, we need a reduction of the coupling to B quarks. And if one looks at the, I don't have the detailed values here, if one looks at the couplings, indeed, BB bar is reduced, and it's reduced to a level that it's fully compatible with this with these measurements here. Yeah, it's not zero, of course. So you don't get zero. You get somewhere, I don't know where you end up, but probably somewhere in this range here. But it's fully allowed. But the fact that you need a coupling reduction to B quarks also for the gamma-gamma mode doesn't make this more or less compatible or incompatible with the rest. What makes it less compatible are the other searches in the tau-tau mode that I was mentioning here.
Right. So, because I was thinking, right, that in your SUSY models, you ditched that tau data, right? And
yes.
Right? So
that's correct.
But maybe it should be the LEP data, the one that could be ditched, right? So that's a...
Yeah, it's always difficult for theorists to pick results. Yeah, if you do this, you can favor one or the other model. And of course, I'm also I can also fall for this. So yeah, I might be tempted to do this. And this is, well, I ditched the tau-tau data for SUSY because it's as good as this one here that I was showing to you. This one, yeah. You can't do it. Point. Period. Yeah, it's
yeah.
If tau-tau is true, well, you can't do it in this kind of models. Of course, you can construct models with more than SUSY models with more than 2 doublets or so. There are 4 doublet models, Supersymmetric, on the market that may be able to do it. I know that some people may be looking into this, but let's say the normal SUSY types, they would all be ruled out.
I see.
So as I was saying before, originally the gamma-gamma value was here at the 0.6 level. Yeah, this was the original value that came out from CMS in 2017 and stood there for many, many years. And SUSY said, we can't get there. Yeah, we can't do 0.6. We can only get to I don't know if this one should be correct. We could get at the 0.3 range or something like this, yeah, but not more. So SUSY kind of predicted that this value would go down, and this is exactly what happened. And therefore, SUSY predicts, but can be falsified. This is the good thing. Can be falsified by the prediction that the tau-tau channel is not right. If tau-tau is confirmed, for example, with a new ATLAS measurement, there's no ATLAS measurement in the low Higgs mass search in the tau-tau final state. If they would confirm this axis, then I would drop MSSM or NMSSM explanations immediately. They can't do the job. It's impossible. Then one has to look at type 4 models or models with more than 2 doublets, making them, in my opinion, less attractive. Yeah, having the minimal models more or less doing the job is already quite some achievement.
Super. Thank you very much. So let's go to the questions from the audience. So we have a question from Omar Suarez. So his question goes like, so is there any reason for this new boson to have masses relatively close to Z and W? And could this suggest that there could be other vector bosons with masses close to the Higgs mass?
Interesting question. but I do not have a very good answer to it. For me, this is a coincidence. Yeah, there's no deeper reason behind. If somebody could explain it, well, only that, I mean, 125 is already, it's the electroweak scale. Yeah, it's everything is proportional to the VEF in the standard model. Yeah, it's square root of, how is it? Square root of lambda times the VEF or something like this. And naturally we get something in the scale, and the masses of the W and the Z are given by the VEF of the standard model times the weak couplings. Yeah, so that we end up somewhere in the same range is normal. And that with this Higgs we end up also in the same range looks normal to me, but it of course depends on how you choose the other input parameters. You can take the N2HDM or the S2HDM and make everything heavy. It's easy. You can just do it. Yeah. So in this sense, there's no reason. It's kind of natural, but I don't know any deeper reason for this. And therefore, I also wouldn't predict any new gauge bosons in that mass range. Yeah. I would in fact be surprised, because new gauge bosons usually couple relatively strongly also to fermions, and one would have seen some hints or so. Yeah.
Yeah, I was thinking that this could kind of like be connected to Nicolas' question, right?
Yeah.
But yeah, it would be difficult.
Yeah.
If they could couple to fermions. So super. Let's go to the next question, which comes from Marvin Flores. So he says, thanks, Sven, for the nice talk. Here are my questions. So he's got two questions. First, does this excess appear in the ZZ star to 4 lepton channels? Right? Since
also very good question. And we've been asked this question before, and then we've looked into the numbers. And those days, the number of events that we found based on our model predictions was around 1 event. And so if it's there, yes, it should be there, but we need much more luminosity to see it. And I do not know, we never investigated this, whether the high lumi LHC might get us to a level where the ZZ channel may be observable. This might be something interesting to look at. Now, nobody did it so far. But yeah, with the current luminosity and also with now run 3, I don't think that we can hope for the ZZ channel. It's just too low, the number of events.
And the second question is if it's possible to have any decays from the 125 Higgs to the 95 plus gamma.
In principle, this may be possible, I think. Although, of course, it would be loop induced. No, well, a spin 1 particle connected to 2 spin 0 particles, I think is not possible. Okay, don't nail me on this.
Yeah.
But so, for example, the standard model, this was never investigated, of course, because there's only 1 Higgs boson. But I'm not aware of any kind of this. No, I'm not aware of anything like this. And it's probably forbidden because of the spin NCP.
Interesting. I hadn't thought about that. Okay, so very good. So we have Omar saying thanks. And probably Marvin will in like 15 seconds when he gets this.
Yeah.
So I don't know if there's any other question from the audience.
I see that Roberto.
Yes, I have a question. Very, very nice the talk, Sven. I enjoyed it a lot. So I have kind of 2 questions, like if it is necessary to have 2 doublets for to have this excess. I mean, this is the first. I mean, let me tell you 2 because they're connected.
Yes.
Could be related in some sense. Could be produce the same signature, for instance, by introducing a Higgs doublet plus a triplet Higgs model, and could be connected with the W mass anomaly. This problem with the mass.
Okay. I can answer. I mean,
it's very
easily. I can answer the second question easily. Let's first get rid of the chat here. Okay, because it disturbs the view. And the first question, so I don't know about a triplet. There are explanations going with the Jones-Perez model, but not necessarily only for this excess, but more with other excesses. So in this kind of model, well, in the Jones-Perez model, as far as I know, it's possible. We also looked at it a bit, yeah. So in this sense, with triplets, you can do it. So you don't need necessarily a singlet. But this is also kind of natural because you have much more freedom with the triplet, yeah. And of course, you have additional constraints, you have additional predictions for doubly charged Higgses, etc. But in principle, this can be done, yes. About the you were talking about the W boson mass, right? And I have something in the backup because we looked at it and we investigated this. I think, let me see. Yeah, this one. Right. This is our model. This is the plain W boson mass versus effective weak mixing angle, coupling of the Z to fermions measured at the Z boson pole. And we did a dedicated scan to get the contribution via the T parameter to get to this infamous CDF value. We know that there is by now a kind of world average or so, which would be somewhat closer. But if you get to CDF, you get to everything in between as well. And one can see here, well, this is the standard model set. These are the two measurements, W boson mass, weak mixing angle from lab, and the same from SLD. This is the world average of the two. And one can see that this is what our model predicts. So it's effectively aligned with the T parameter going here. And yes, one can get higher values. And the reason is that we mainly work here for the 95 with a singlet, which is mainly singlet-like, and the standard model like Higgs, the 125. The heavier Higgses are kind of independent. And so you can arrange them in a way to get larger contributions to the T parameter, which then gives you, I can show this, I have the formula here. This is the formula to the rho parameter, which is T parameter times alpha. You can get these corrections with the heavy Higgs boson masses. You see only the heavy Higgs boson masses enter here, and then you can get the correct value easily. If you want to end up here, you can also end up in between wherever you want. It's possible, no problem at all. So it doesn't give you any additional restrictions or predictions, I would say. It's just possible.
Okay, thank you.
Okay, we have another question from Nicolas. And before that, Marvin says thank you also.
Yeah, thanks.
Okay, thank you. So I was wondering, choose the two Higgs doublet model plus a singlet. It's not possible to fit this excess with a, for instance, just with a two Higgs doublet model, or just with a singlet and one doublet?
Yes. The simplest thing would be, let's go back, would be standard model plus a singlet, right? But if one looks at this, here the two Higgs bosons that you have, they have only one mixing angle that, mixes them. Which means that the couplings to tops and bottom quarks always goes in the same direction. There's no way out. All the couplings are reduced with the same sine or cosine theta, depending how you set up the model. So this model is too simple. It can't do it. Two doublets is something that we looked at in the beginning, and we found that we really need a large singlet component of the light Higgs boson to do a proper job. There are a few papers looking at it. There was an original paper that used Higgs doublet model type 1, but with a different production mode, which looked very contrived to me. This was by Uli Heisch and company. And then recently, my collaborator Thomas, with a Portuguese group, they looked at the complex Higgs doublet model, where they could do it to some extent, but if I remember correctly, not as well as we could do it here in our singlet extensions. Yeah, I don't know whether Thomas wants to add something here, if he's still here.
Apparently not. Oh no, here he comes.
Yeah. Sorry, it took me a minute to turn on the camera. In the 2HDM, you kind of the excesses you can do, but you have tensions with indirect constraints from flavor observables and from EDMs because you need the CP violation. So there is kind of a tension with these indirect constraints, as I said, but this is why these 2HDM plus singlet extensions are kind of easier because you can avoid these issues.
Okay. And even within this model, well, 2 Higgs doublet model plus singlet is important for the singlet to acquire a VEV. Could you just make a no VEV for this guy?
Oof. I never looked at this, I have to admit. As I said, I think in the N2HDM, if you don't have the VEV for the singlet, then the additional scalar, because of this additional Z2 symmetry, is a dark matter candidate. So this wouldn't work. But you can, of course, neglect then this Z2 prime symmetry, which is a different incarnation of the 2X doublet model plus singlet. Then it may be possible again, but I didn't look at it. There are many variations that are quite subtle. Yeah, the symmetries that you have, as said, the VEV that you have, whether you have real or complex singlet. Yeah, there's a plethora of models you can investigate. But I would be happy to see this. Yeah, I'm not aware that anybody did it.
So in this sense, of course, the VEV breaks the Z2 symmetry, but you're also adding a soft, explicit breaking term.
Well, there are two Z2 symmetries. Maybe I go back to this slide. One Z2 symmetry is included to avoid the flavor change in neutral currents. Sorry. Yeah, so this is the first Z2 symmetry that is always there, except that in the 2X doublet model, of course, this here doesn't play a role. You only have this one. And this one is softly broken by the M12 parameter, which is shown here via this term. But this at the tree level doesn't induce flavor changing neutral currents. Yeah, it breaks the Z2 symmetry, but it's said softly because it doesn't introduce this kind of flavor change neutral currents at the tree level. And then this is the second Z2 symmetry that in the N2HDM is usually assumed for historical purposes, I would say. Or the model that has this Z2 prime symmetry is then called N2HDM. If it doesn't have the Z2 prime symmetry, I don't know how it's called. But as I said, there are many, many models like this on the market. There's also the 2HDMS, which has a Z3 symmetry instead of the Z2 prime symmetry. Also, so there are many models on the market.
Okay,
Thank you very much.
Super, thank you. Let's see, we don't have any other question from the audience, from the YouTube channel. I don't know if there's anything else from the audience. We're a bit past the time, but if there's any urgent questions. It seems not. Okay, so we're good to go. Well, I have more questions, but I can do that offline. So thank you very much for the very nice talk. And yep, let me remind all viewers that we will be back on the 8th of November with Basabendu Barman giving a talk in dark matter, I think. So thank you once more, and we'll see you around.
Okay, see you. Bye-bye.